Okay, so like I said, since you guys are doing, I don't know what your background, but I assume some of you are researching like a structural performance. Some of you are researching the water performance, like oceanology or coastal engineering. And some of you might be doing construction. But anyway, time series data analysis will be very common in terms of research and how to extract features from time series data and to further predict the behavior of a structure or some material, for example. So this is a much better view of that. So if you look at from this direction, look at this graph, this is called a time domain, right? So this is time, and this is basically shows the magnitude, amplitude of vibration. So the spectral analysis assumes that any random vibration can be decomposed into the linear combination of a set of same vibrations, regular vibrations. And so the linear combination, the coefficients is actually considered as power of that. So now you can imagine we decompose that in this way. And from the powers, I believe like this frequency is strongest, this is the middle, this is the shortest. If you do this linear combination, you can definitely get this curve. You can imagine that, right? And this now we convert this from time domain to what we call the frequency domain. And the coefficients for the linear combination is called the power. Like from here to here. Makes sense? So this is how we extract the features from time series data, but all this is how our ear hears things. You know, like when you hear music, the music is a pure vibration, right? But our brain basically decomposes that into different frequencies. So sometimes that's how you differentiate a male's voice from a female voice. Can you guys tell me why? Because female's voice will contain more high frequency vibrations. So the power for this one will be bigger than the power of this one. Make sense? So then our brain receives this kind of information. Our brain is doing a lot of conceptualization and abstraction. Our brain basically reduces the data and only focus on the feature. We'll be talking about that. So our brain can tell things so easy. Like how we see things, how we hear things, how we understand things. That's a result of evolution, you know, because we are receiving so much information from the world, we cannot digest or comprehend the raw information, raw data. So our brain actually develops the ability to extract the features. And then the computer science guys, they just learn from how our brain understands things and develop all the deep learning algorithms you're learning. I'll tell you this. The most popular deep learning method called a convolutional neural network. Actually, that was inspired by how our human eyes see things and understand things. So we'll be talking about that while we cover the machine learning part. Very interesting. I also found this video, very practical video to show how people were using this spectral analysis understand to perform the signal processing. So let me know if you can hear the sound of the video. Can you hear the sound of the video? No?
No.
Let me see. I think I shared this. Share computer sound. Yes. How about this?
Where every signal, beautiful property of
Can you hear the sound?
Yeah, yeah.
Is that clear?
Every signal can be thought of
Okay.
as
Okay. Let's do
property
it.
of mathematics. Where every signal can be thought of as the sum of a bunch of sine waves.
Did you hear him? He said every signal.
Any signal you want, any shape, name a shape.
Let's do a square wave.
Square wave. By coincidence, that's what's on this next card. Yes, Tony, even a square wave is the sum of a bunch of sine waves. Let's see how that works. If we wanted to make a square wave by adding together a bunch of sine waves, we'd start with a single sine wave.
Ooh, how smooth.
Yeah, very smooth. It's almost like we've done a bunch of failed takes of this video.
No way. This is the first.
So if we add a sine wave to nothing, we get a sine wave.
Okay, 1 to 1. I got it.
Right. And that would cause a single spike to appear in the frequency domain. now we're going to add a second sine wave that's 1/3 as tall, and it's been scaled in by 1/3.
And this is the mathematical part. This is like, there's two humps within this big one. All the way
Yes,
across.
exactly. When we add those two together, that's going to add a little.
Yeah.
As you say, that's going to add a little hump at the top and bottom of each of these. And in the frequency domain view, because it's two sine waves, that's two peaks. So let's add a third one. Instead of this one being scaled by a third, it's scaled by a fifth.
I see
And when we add that, it's going to add even more wiggles. It's going to make the sides steeper. It's going to make the tops and bottoms flatter. And you notice we're kind of closing in on a square wave here. So then we go to
Did
a
we say
seventh.
we're getting squared up here?
Oh, terrible.
Okay.
We go to a 7th and 1/9 and 1/11 and so on. And so we keep adding peaks until it kind of vanishes down into the noise floor.
Oh, yeah. And we recognize that. That goes down like that.
Now let's hang on.
That makes sense, right, guys? So the spectral analysis or the first Fourier analysis is actually doing the upside. So now you have this random curve and random vibration. How can you decompose that back into the regular sine waves? So now I think it's time for you guys to link what you learned from the advanced mathematics to the engineering applications. I'm pretty sure everybody learned the Fourier transformation. That is the one that you have a lot of derivatives and with whole lot of functions plus some final term. Recall that? Now, that is exactly the method we are using to decompose that. Now it makes sense, right? I saw some smiling face. That's great. All right, so that's the, let me see where we are. Yeah, so that's basic definition, the biggest difference between the information system and the information technology. I believe the rise, like more definition things to the last module, when we talk about the information strategy for a company, because now assume you are IT consultant and you are suggesting some kind of strategy for a construction company, and you have to consider how to change each of the components, the hardware, the software, the database, and everything. So that's something I think it's better to cover later. So now let's move to the next, let's move here first. Information technologies in construction. So we talk about, I think you guys now have a sense like what's going on with, different steps in this information system, like from data to information. Okay, so let me see. Yes, so I basically listed, based on this framework, we know that what we need for each of the steps. For the collection, which is the data level, our goal, or what we are trying to do today is how to make it automated and more efficient to collect a great amount of raw data. So all the technologies you're seeing, like the barcode, RFID, the sensing technology, scanning, photogrammetry, drones and the use of UAV, mobile phones, smartphones, and big data. That's all about how to collect data automatically and more efficient. And mapping, this is about to, let me switch to my, oops. Sorry guys, give me a moment. You guys can hear me, right? Okay, so the mapping, we talk about the computerized project management, like the cloud server, the cloud sharing tools, and web-based applications, and the use of smartphones to log everything, log data. That is actually how we assign a meaning to the raw data. And our goal is to make this process more effectively, which means we don't want to map the raw data into the wrong label. Like if we see somebody is doing something, we want to label it if this is a safe behavior or not safe behavior. So we want to do it correctly, more effectively. And the learning, we want to make it more precise to generate useful knowledge based on information. So that's, we see the expert system, knowledge-based system, business intelligence, and the use of building information modeling. that is more about now we have a lot of information from the project. Can we get a high level understanding of what's going on? For example, the overall cost overrun, the overall status in schedule, you know, that's all that's all why we are developing these technologies. We want to precisely generate the useful knowledge based on all the information we have. And finally, the reason we are using machine learning and deep learning today is we want to intelligently make good decisions. So we want to run the machine learning and everything for that. I think I prepared this quick matrix ID applications. So if this was not a online course, I would have like a big whiteboard and ask you guys to come here and write things down. But now let's just do this quickly virtually. So we have the 4 functions: data collection, information mapping, knowledge management, and wisdom. And we also have different phases for jobs, for construction project, like from design to contracting, the bidding process, to construction operations, and to finally to facility management. Can you guys name some technologies that serve the functions here to fill out the matrix here?
A seismograph for areas where there's earthquake.
Sorry, what's that?
Seismographs for where there's places with earthquakes and stuff.
Okay. What else, guys? Anybody else?
Maybe data of like the weather conditioning there for the design.
What's that? Sorry.
Like in the design phase, maybe we could collect the data of the weather.
Okay. Design phase
Of the load analysis, maybe.
Okay.
Some sort of a statistical module which provides info about a particular data, for instance, movement of traffic in a particular roadway.
Okay, that's also for design or construction, right?
Yeah.
So maybe I can also propose something. So for example, data collection for construction, we can use human carrier sensors like IMU. We can also drone to collect information to support the construction operations, right? So for the facility management, you know, we could have some sensors to track the building occupancy, to track the use of AC, to track the use of electricity, right? So that's all good indicators for preventive facility management, you know, to stop the problem before it happens, right? So for wisdom, for example, for construction, you know, we could be using some kind of a machine learning algorithm to tell if we have enough materials to support the next week operations, or we could use, you know, some prediction methods to predict the labor needs. So we know if we want to delabor or if we want to recruit more temporary workers to support that, right? What else? Let me think about something related to information mapping. Definitely, I think building information modeling, you know, that's a very popular, like a visualization or virtual design. That is something related to design, but I think it serves the function for map the information better and also management the knowledge better. So now you have a centralized place, so you can integrate all the cost of the materials, equipment. You can integrate the duration for each major components. You can integrate things such as the material properties, PSI value, insulation, you know, all information into the same place. So that will support you to make a good decision, right? So we support you to understand the situation. For example, one thing I want to understand is by looking at a model, I know how much dollars it will cost. So that's actually something more than the data collection, right? Any more comments? If not, we are going to move to our next topic for now, which is big data. All right. So this is agenda for that. You know, we want to introduce what the definitions and the basics about the big data, and why do we need a big data paradigm today for construction, and also the main big data tools, you know, like the MapReduce method by Google, like how we are processing big data. But to understand that, you have to understand big data is fundamentally different than data. You know, it's not like you copy paste some numbers in Excel spreadsheet and it can do some quick matrix calculation, some quick mathematics. No, because big data is too big, and none of the tools we are familiar with is useful. For example, if you guys want to sort the thing, sort the numbers based on the value in Excel, that's very easy, right? So you just basically click one button and there's a little triangle and you can basically do things like that. But I can tell you, sorting the numbers for big data by itself is a great challenge that a lot of technology companies are trying to resolve. It's because it's too big. Amazon, for example, they want to sort their customers based on the buying history, like how much dollars is spent last year. Think about how many customers Amazon is having. We are not talking about like millions of customers. We are probably talking about potentially billion customers. And if Amazon wants to sort that, think about the difficulty. Can Amazon just copy paste all the numbers in Excel spreadsheet and do the sorting? No. So that's why they have very specialized tools to do that. That's why big data is very famous, very interesting research area. So the first time that I understand the challenge of big data was in 2014. I attended a conference, it's IEEE ACM conference called the Winter Simulation. So the keynote speaker was the I think female FamiLab director. I think he was a associate director, Robert Roser. So he introduced the project called Higgs boson particle project. Do you guys know what the Higgs boson particle, the Higgs particle, the God particle? So basically, it shows that why there's a mass. You know, it is the key step from moving from energy to mass to something. You know, mass means something has a mass. Or on Earth, that means has a gravity. But think about that. Why things have mass? That's the Higgs particle. So all the particles, when Higgs particle appears, all the particles will come together and bouncing together. And they come together, bouncing together is actually the source of mass. You know, that's actually a very interesting concept, but we need to, it's a theory that is working by itself, but we needed to discover, we needed to get empirical evidence for that. So that's why the Large Hadron Collider in Europe, LHS, played a very important role. So this is actually, they gave a lot of huge amount of energy to the small particles and accelerate the particle to almost the speed of light and ask them to hit each other. And by doing that, we can basically, you know, destroy the structure of the fundamental particles, see what's inside. And hopefully we can discover the shadow of a Higgs particle. So that's what's going on. So basically the keynote speaker described that project. They hired more than 10,000 scientists and engineers from more than 100 countries to support that project. And the construction of that actually took them 10 years, from 1998 to 2008, and costed them more than 10 billion euros. That's a big project, supported by 140 computing centers in 35 countries. Every second energy consumed in this facility equals to 175 kilogram TNT. So just think about the magnitude of this one. One thing that he introduced, and by the way, this is how it looks like. The diameter is almost 9 kilometers. That's actually a small tongue. You can see the tongue is actually built in the middle of that. And I think the depth is, I cannot recall the depth of that. Oh, it's 175 meters. So that's the size of that. It's actually underground. And this is how it looks like. This is part of it. And this is the channel for the high energy particle to travel. And that's humans. That's people. You can now see the size, the magnitude of this. One thing that surprised me was not this project or the fundamental theoretical physics was actually the data processing need. And the data processing need actually costed almost half of this project. So half of the cost actually went into the build the data infrastructure to process the data. So I found this video. Oh, where's here? So I guess I will need to unplug my earphone again.
Grammarly does more than catch errors. With Grammarly, you can find really good.
You guys can hear it, right? All right, so I hope this can give you guys of a sense that how big data looks like for the modern scientific and engineering discovery. The reason I'm showing this example is this is probably one of the most significant project that uses a lot of big data analytics. But do you know who is generating a lot of the biggest amount of data today? You guys, everybody. So we'll be talking about that. Actually, everybody, we are generating unprecedented amount of data. By the way, this is how Higgs, just a little bit of science here. This is how Higgs performs, you know, like other fundamental particles, just, you know, there's no need for them to bond together and to form things, let me put it that way. But when Higgs appear, then all of a sudden, all the other fundamental particles will come together and so they start to form the quarks and the neutrons and electrons. And so that's how we start to have all the particles. And that's why we have mass. That's why we have things. That's the building block of the world. And there's an interesting background of the name, about the name. So journalism was asking Higgs, you know, the original one who proposed the theory and directed all the experiment, like, do you have a name for this? And he actually told the journalism, this is called a goddamn particle, you know, because we couldn't find it. And the journalists removed the word damn, so it became the God particle. All right, so this is about big data. And what is the biggest challenge facing LHM? Let me check this video quickly. Sorry, we have to wait for the commercials to finish.
First of all, where you want to see the court take the country. And secondly, what's your view on how the...
Yes, this is the video we just played. All right, so how big is big data? And that's the key word for big data. Okay, you guys now probably know this, right? So we have KB, MB, GB, and today a lot of you actually know TB. And every time it doesn't increase 1,000 times, it increases 1,024 times. You guys know why, right? So this is how we started. And this is why 1 bit, you know, this is actually about the mathematical system we use to store information. So 1 bit is actually 16, you know, 8 digits, right? So and that's why it doesn't increase by 1,000 times, it increases by 1,024 times. But in general, it's about 1,000 times. You can imagine that. So, but TB is definitely not the upper limit. So we also have a PB, the petabyte, that's almost 1,000 TB, and 1,000 PB, we call it actual byte, that's, you know, EB. And we also have a zettabyte, that's 1,000 EB. And we also have this 1,000 GB called a yottabyte. So every time the power just increased by 10. So it's 2 to the power of 10, 2 to the power of 20, all the way to 2 to the power of 80. So this is very abstract, but let me show this one. How much data is generated every day. So Google processed 3.5 billion searches per day. That was old data in 2018, 2 years ago. So they processed 3.5 billion searches. Facebook has 300 PB data in January 2019. You guys still know what PB mean? So let me show you PB here. Okay, so 1 PB is actually 1,000 TB. All right. But think about that, just about 10 years before that, so the number was only 2.5 PB. So Facebook is actually generating, every one of you is generating a lot of data. And the CRN, that's the LHC, actually generates 15 PB data a year. So now just think about the magnitude of that project. So if we use the number for Facebook in 2009, that is actually about 6 times, right, of the Facebook total data in 2009. And that includes all the videos, all the posts you submitted, you posted on Facebook. So together today, we are creating about a 2.5 quintillion bytes of data per day. And I just write it down like this. How many zeros? I don't know how many zeros, but now you know the size of that. That's how much data we together are creating on a daily basis today. Ironically, this guy said this, 640K ought to be enough for anybody in 1982. Now you can see how much we changed just in the past 3-4 decades. This is Eric. I think he's still the executive chairman of Google, right? I don't know. So basically his side is, from the dawn of civilization until 2003, humankind generated 5 extra bytes of data. Think about all the civilization, all the history, all the mid era in Europe, okay? Now we produce 5 extra bit data every 2 days, and the pace is accelerating. I think he gave this comment like in 2013, and I read the latest data. It shows that 5 extra bits every day, so not every 2 days. So think about that every day, from you getting up in the morning to you go to bed, we actually generate the entire human history. Okay, that's the size of that, and extra bits is here. Okay, so that's 1,000 PB. And this is the data never sleeps visualization. And you can definitely Google the latest one. It shows that the different social media platforms or different apps, how much data they are generating on a daily basis. You know, the Uber riders take, what's this? 45,000 trips. Americans use 2.6 million GB of internet data on this is every minute, guys. This is not every day. This is every minute. Americans are using 2.6 million GB of data. Let me see what else we have. So Google, every minute people actually search, conduct more than 3.6 million searches using Google. And this one's interesting. So every minute, the entire world receives more than 100,000 spam emails. YouTube, you know, people watch more than 4 million videos every minute. Snapchat, LinkedIn, you know, very interesting data. You can definitely search yourself. Okay, so I would love to use this, you know, to help you understand the keyword big. We have to visualize it. You know, that's the only way for you to understand how different big data is from regular data. So I was thinking the use of Excel spreadsheet. You know, in Excel 2010 version, the maximum worksheet size is almost 1 million rows by 16,000 columns. Okay, so if you keep adding rows, you can add up to 1 million something rows and 16,000 columns. That represents about 16 GB, you know, data. And the limitation for the early version of Excel, the XLS, is actually only 256 columns and 65,000 rows. That's 16 megabit. So the newer version can store 1,000 times of data compared to the old version. So how much data we are creating on a daily basis? So let's think about print all the data on Google Excel spreadsheet. So the amount of data we are creating on a daily basis equals to 1 billion columns plus 20 billion rows, full table. So that's actually a giant Google spreadsheet. So if we are using the 2010 format, that means 1.2 billion printed piece of papers. Now, if we print the entire thing, you know, I'm thinking about you are printing like 1 million lines on a single A4 or lighter sized paper, which is impossible. But let's assume that's possible. So let's print really, really small font size and 1 million lines of data, we still need 1.2 billion piece of papers to print the data we created on a daily basis. If we are using 2007, then we have to use 1.15 trillion Excel, piece of papers. Okay. Oh, unfortunately, I had this thing. I'm so sorry. Okay. This is how much $10,000 look like. You wouldn't imagine $10,000 is a lot, but unfortunately, $10,000 just look like this, right? This is very small. Imagine how much $1 million would look like, guys. Can anybody let me know, like what, like something you put in a truck, a suitcase? Okay. This is only $1 million. I'm so sorry. You can easily put in your backpack and you can still insert all your other stuff like your laptop, whatever, notebooks inside. $1 million is only this much. The average income for American engineers, I know you guys will become engineers. There's a data showing that the average income, the lifelong income for you guys would be about $2.5 million to $3 million. So just imagine your entire life is only 3 packs of that. So that's $1 million. So $100 million, that's a lot, right? We don't know a lot of people owns $100 million. So, but it's very easy for you to see that, it's just $100 million. So what is $1 trillion? This is not even $1 trillion. This is actually, I found this one, but this is only half of the $1 trillion. So this is the same person, okay? And this is actually the $0.1 trillion. Let me show you this. And we need a $1.15 trillion, which means twice of this one. So now imagine we could print that entire Excel spreadsheet on just $100. That's not even the size of a lighter size piece of paper. It's just a bank bill of this size. We still need this much dollars to print the entire data we are generating on a daily basis. Now, guys, if I ask you to find the maximum value from this chunk of data, is that an easy task? No. That is why when we add the name big to the data, we totally change the way we process data, we analyze the data. That's why we have the big data analytics. Okay, so this is I don't know why I keep going back to there. This is actually the video showing what big data means.
So we constantly produce a lot of data, for example, via social media, public transport, and GPS. But it goes way beyond that. Daily, we upload 55 million pictures, 340 million tweets, and 1 billion documents. In total, we produce 2.5 quintillion bytes a day. That's a lot of zeros. It's ridiculous. We call this big data. But what's actually more important is what you can do with it. To process big data, you don't need huge computers. People work with the cloud, an endless network of normal servers, and powerful algorithms. This way, they can analyze over 1 million pieces of data in minutes. And the result? Well, for example, video streaming website Netflix analyzed the big data of their viewers, like popular shows and watching patterns. This way, they produced a successful series with the perfect combination of actors, directors, and storyline. Right now, the big data of traffic is being analyzed to develop a car that can drive completely accident-free all by itself. And in the future, we can even use the big data of DNA to determine the perfect treatment. This way, curing genetic diseases like cancer would become much easier. And that's just the start.
All right, so I hope you now can sense what the big means. Okay, so now we're actually at the dawn of big data. Maybe it's too late to say that. I have to say the big data concept started to emerge about 10 years ago, when people start to notice the importance to learn from big data. This is about from data to information. we know this is a valuable asset that we have, and we can definitely generate a lot of knowledge from it. It just we didn't have a lot of tools at the time. So that's why you start to hear cloud computing at that time. So everything is connected. The reason we have cloud computing is actually we were running difficulty of storing huge amount of data and analyzing the huge amount of data. So that's why we started to develop new technologies for that. So there are some things that are so big that they have implications for everyone, whether we want it or not. So big data is actually one of that things, and it's totally transforming the way we work and we live. So the basic idea behind the phrase big data is that everything we do is increasingly leave a digital trace or data which we and others can use and analyze. So big data is there, we can learn things from there, but we have to use the proper tools. For construction, maybe you would think construction is not a perfect example for big data, but I have to say, given the new ways for sensing, like new sensors, new cameras, we also generating lots of data, web-based data, the management software we use for construction, and also the imagery data collected from the drones, the daily logs, also all the design data, the personnel data. So that's why we start to see the increasing use of big data to support the construction, engineering, and management. So what types of data can be considered as big data? Big data is not just numbers. For example, the camera views of construction workers, that's also considered as one type of big data. So by definition, we have 5 types of data for big data. Relational data, such as the tables and the transactions, something moving from one party to another party. Text data, such as words, the natural language, like the emails you are sending to a general contractor, that can also be considered as the text data. Semi-structured data, it's not perfectly structured, but we basically organize in a way. For example, the extensible markup language, XML, that's a way to mark up the useful information and to semi-structure the data. For example, building information modeling is actually uses XML. What do you see as the 3D models, as the 3D components in the eyes of the computer is actually just a lines of numbers. And the way it organizes the lines of numbers is actually using XML. So for example, there's a label showing, now I'm going to describe this column. And following that, this one shows, now I'm going to describe the dimensions of that, X equals to what, Y equals to what. And now I'm going to describe the material of that. So this is concrete. So actually that's how they label things up and using the XML language to process the information. It's just at the front end, the user end, we convert all the XML metadata into something like a 3D model. Graph data and the streaming data. Graph data is actually what we call the semantic web data. So like, for example, images, videos, that's all can be considered as a graph data. We call it semantic web is the data itself doesn't have any meaning. We have to label them, that's called a semantic. And there's also a bunch of analytical methods called a semantic web method. For example, RDF. This is about how computer can recognize this is a running car, this is a moving person, this is some construction equipment by labeling things. And there's a rule related to that. Streaming data means you can only use the data once and the data will be gone. So it's not like the data will stay there, wait for you to analyze them. All right, so why big data is important? I guess I will leave this, this thing later, but let's talk about the definitions of big data. What data can be described as a big data? This is a definition given by the literature, and this is actually the standard for describing big data. But one thing the most interesting comment on big data is in is much faster than out. So, I attended I think that's also a vendor simulation conference. I was asking a guy who is doing big data research and asking him, if you have to use one single sentence to describe big data, how would you do that? And he said, in is much faster than out. That's big data. So you understand that? So the way we collect it is so convenient. So we are collecting a whole bunch of data, but we still don't have the necessary tools to analyze them. So we have a huge backlog of data. But by definition, we define 4 V's. That's the 4V definition for big data: volume, velocity, variety, and veracity. So the volume actually refers to the vast amounts of big data. So it's big. That's why we call it big data, from all the KB to MB to TB to PB to EB, right? So we are not even talking about TB, but potentially GB or 1000 GB, that's a BB. So I think I mentioned that actually we are generating more data on a daily basis than the entire human civilization until 2003. And the reason is 2002 was considered as the turning point, the beginning of the digital era. And this one shows the percent of digital information. At the very beginning, only about 1% information could be considered as digital. But now the most of the information today actually are considered as digital information. And this actually shows the magnitude of the information growth. Velocity, that's the second feature of big data. Like I mentioned, in is much faster than out. It refers to the speed at which new data is generated and the speed at which data moves around. So just think about the social media. If I want to understand the human mobility, human mobility refers to how people move inside the city. And the people today are using Twitter data and social media data to check, the geo information of their threats and to understand the moving pattern. A big problem for those kind of researchers is, again, there are new features generating every second. There are new data generating every second. But the methods they are using, the machine learning model, they are using the Python, the TensorFlow, just cannot digest that kind of fast input data. So every time when they believe they find out some pattern from their data, new things happen. I don't think they have an answer yet. And by the way, I'm working on a project right now, NSF funded project, try to understand like how COVID-19 is affecting the human mobility. And also that's also our challenge. Like we just couldn't figure out a way to understand the real-time mobility pattern. Because every time when we consider it's real time, next second, we receive the same amount of data from all the social media platform. Variety refers to different formats and types of data we can now use. Not structured, not just numbers. In fact, 80% of the world's data is unstructured, such as language, text, image, videos, and voice files. So another challenge for the big data analytics is how we can convert the raw data into digits. Because like I said earlier, most of the algorithms and the models, data analytics only work with numbers. So if I'm receiving like a sound file, a voice file, or image, I have to figure out a way to convert that into numbers. But I don't want to just convert a raw number because that will take a lot of storage and also will make the data transfer extremely difficult. So there's also a research area at how we can translate other formats of data into digits. So by itself, that's also a very interesting research area. Veracity, that actually refers to the bias and noise and abnormality in data. Like when we store data and transfer data, we will definitely have errors. So how we can figure out the errors, how we can avoid errors, that's one thing. And also there's a increasingly popular topic in big data literature. It's called the fairness in data. So basically it shows that, for example, when we study the urban mobility, we want to collect information from the smartphone use, right? So smartphone can track your GPS. So that data will tell us something, information about that. But then people figured out, because of the different social economic status, a certain group of people don't have access to smartphones. So they just literally don't have smartphones. So now imagine you have the world most wonderful algorithms to analyze data, but you just don't have enough samples from certain group of people. So NSF is actually forming a couple of new programs called fairness in AI and fairness in data, try to solve that problem. But once again, this is an extremely challenging research area because we don't know if the data we have today is biased. So that's actually the four V definition for big data. And talking about the forms of big data, the contents of big data that could be relevant in construction. So one thing can be activity data. You know, if there's a way for us to use the human character sensors and also the logs like RFID to track human activities on not a daily basis, not hourly basis, but maybe every minute or maybe every second, that amount of data will be very informative, but also very difficult. By the way, so for certain projects, the schedule is actually the unit for the time unit for the schedule is actually seconds. Does any of you know what kind of projects will require second-based schedule? That's also engineering projects.
Maybe nuclear projects, maybe.
What's that? Sorry.
Nuclear projects.
Yes, exactly. Nuclear projects. So for the nuclear turnaround project, their schedule is actually based on seconds. So now imagine the difficulty of running a resource constraint leveling scheduling analysis, like how I can move people around, right, using that schedule, because the magnitude and the complexity of that schedule is significant. Conversion data, you know, we are talking about human natural language. So we are talking every day, right? People are talking to each other and we are sending emails. Unfortunately, when we send emails, we use natural language. We don't just fill out some tables or some terms. Would you think that's a useful source to infer what's going on with a project, guys? Definitely yes. What is the formal way to exchange information for construction project? Like, I believe something's wrong, so I want to document that and I want to share the information with others. What is the formal way to do that? It's called RFI, request for information. You guys have heard about that, right? And do you guys know the average turnover time for one RFI, which means I send out the RFI and I receive the response from somebody? That's a formal form. You know, it's a standard way, most standard way to describe the situation. Do you guys know the average turnover time?
I think maybe 14 or 28 days.
It's 10 business days, 2 weeks. That's actually based on the survey. So does that mean that we are exchanging information for a project that at a such slow pace? No, because that's the formal way, but we also use a lot of informal way, like phone calls, like emails, right? That's actually a good source of data. And that's why this bunch of researchers from Virginia, I think originally from Virginia Tech, now this John Taylor is with Georgia Tech. They actually developed this natural language processing and to analyze the messy talk. So what they did was they actually went to the meetings with general contractors and subcontractors, and it basically videotaped, audio taped all the conversations, and applied the natural language processing, NPL, that's a machine learning algorithm, to extract the keywords and also the logic from there. And if you have a good model, that thing will basically list, for example, the list of change orders for you. So just by analyzing the chat, they list all the change orders from there. That's called a messy talk analysis. So it's possible if we use the proper tool, some source of data that traditionally was not considered as important data would be useful in the future. Imagery data, this is a point cloud. Once again, this is from my niece research group, so I'm just going to play this quickly. And this one shows that we use a scanner to scan the structure. So the one we got is called a point cloud model. The point cloud model means we don't have the mass of the model, but we have a huge amount of points to show the geometry of the model. And this one shows that how we can use it to analyze the progress, identify the issues. And by the way, I mentioned earlier, this guy is actually having a company, he's have business in this area. So now you can imagine how important it is to general contractors. What he is going to show you is how he was overlaying this scanned data, scanned model with the original design. And then by running a machine learning algorithm, so this one could tell automatically the progress of the project. Yeah, this is our original model, and this is scanner model. So we basically overlay them and run some algorithms. It tells you the earned value and also the deviation from the original plan. Now imagine the scheduling process can be made visually and automatically. Okay, guys, so I'm going to stop here just for a moment. All right, so it looks exciting, right? You know, think about in the future, if I get a scanner and scan things and I just import the original design and run some algorithm, all of a sudden I know how I'm look at, you know, how I look like in terms of schedule. What is the challenge here? Can you imagine the biggest challenge that when we are running this kind of analysis?
Maybe to link all the items.
Like a synchronize or match up the models, that's okay. You know, we do have some automated algorithms to run it, or we can just manually find the control points and synchronize that. So that shouldn't be a big problem. Think about others. I think you attended my BEAM class last year, right? And some of you attended that. You guys recall that one team was using the LiDAR scanner to scan just a small room? And I don't know the size of the room. I think the size was only about like 100 square foot, so it's really small room. Remember that? Do you guys know what's the size of the point cloud model scanned from that room? 300 megabit. Now imagine, like I said, this is called a point cloud model. You see the shapes, but it's actually a whole bunch of points. We didn't use the highest standard to scan the room, and it's a very small room, but the size was already 300 megabit. Now imagine scanning the entire building here. It's the entire project here. So I want to say this is a beautiful dream, what Dr. Mani is doing. But I don't think this is usable. Why? In order to get this level of work, he probably would need to scan it at least from 5-6 different locations, you know, to make sure there's no occluded areas, no obstacles. And given the size, I would imagine for each of the scan that would be maybe 5 to 6 gigabit. That's actually a very regular size for the scanner models. Now, if you combine 5, 6 together, maybe we are talking about 30 to 40 gigabit. And then if you need to run the comparison algorithm, that probably would take you, I don't know, maybe 2 days to finish that. So is that possible for some construction manager to get an iPad and go to the site and get that earned value conclusion within 1 hour? No. It probably would take them 1 day to scan things, 2 days to process the data, like to to trim the data, to remove unnecessary data, because it's huge. They had to use the, they probably cannot do the modeling clean with their personal computer. They probably have to use it with, they have to do it with a high performance computing center at a UIUC, something with the cloud. And it probably taken them another 1 or 2 days to run the analysis. So we are talking about a week to get the numbers, and a week manually, we could also get the same answer, right? So that's actually a good example to show without good big data tools, the beautiful dream just cannot be realized. All right. So that's actually the imagery data. That's one part of the things we are talking about. Sensory network data. So imagine the smart building. Imagine the Internet of Things that we have all the sensors to track the temperature, occupancy, energy consumption, thermal performance of the building. If we have all that of data, we can definitely make this building smarter. Okay, so that will be one of your team assignment. How would you add smart sensors to a warehouse and to make it a useful function? But we can definitely imagine that. But I guarantee you, even though you can successfully deploy all the sensors in warehouse, the number one challenge is Wi-Fi here. I'm not saying that a warehouse does not have a good Wi-Fi. Of course, warehouse does not have a good Wi-Fi compared to other buildings on campus. Even if it has really good Wi-Fi, we are talking about potentially hundreds or maybe thousands of sensors tracking data, not every second. A lot of sensors track 5,000 data points per second. For example, vibrometer, accelerometer, because this is vibration, right? So if we say it tracks 5K hertz vibration, it means 5,000 points per second. And we have to send all the data to some kind of a server to process, to predict, to run analysis. Now imagine the size of data you are sending. And I'm talking about maybe 300, 400 such sensors. It is so far still impossible to do it. Not only because of the sensor technology, but also about the telecommunication infrastructure. Do you know what is the latest solution for that? Think about that. If you were an electrical engineer, if you're a researcher in this area, and you understand the amount of data you are collecting and the challenge of sending data to the server, what would be your solution to that? Can anybody tell me?
Maybe divide the data to different computers, maybe processors.
Send them to different computers, is that? Okay, so maybe you have some hierarchical, it's very close to the answer. Hey guys, I'm trying to wake you up. Can any of you tell me the answer? Wake up, guys. Nobody? Okay, this is a concept called edge computing. Basically, you can imagine that if this is camera collecting all the imagery data, instead of sending all the imagery data to the cloud server, I have a chip. I have a very low performance CPU built inside the camera. So it will perform some pre-screening of data. It will basically remove all the useless data first. And if we detect something interesting, it will only send that data of interest. Make sense? So let's say if we add a small chip to an accelerometer, and because the building is vibrating all the time, people are moving all the time. If I'm using this vibrometer to track the structural performance of this building, it will only send the abnormal data to the server. But think about that. We have to make it smart to know that. We have to make it smart to know, to make a judgment, this data is normal, this data is abnormal. So we have to add small chips to all the sensors. That's actually the most promising solution to solve the telecommunication need for big data, for Internet of Things. It's called edge computing. And this kind of a network, we don't call it cloud computing or cloud network. We call this fog network. I don't know, think about the cloud is up high, right? So that's basically we send our data to a centralized cloud server. So fog computing is more kind of like we are inside that kind of computer structure. Every single terminal, every single sensor is actually a sensing unit plus a computing unit. So actually we are in the middle, we are inside this computing server. That's why we call it fog computing. Those are fairly new concept today, edge computing and the fog computing. Make sense, guys? Question? No? Okay, now imagine for your future application, like if you want to make your job site smarter, or your building smarter, what kind of computing structure you want to build? And one thing you also need to notice is the cost. Of course, the fog computing and the edge computing can make things easier, but like I said, you are going to add the CPU chips to all the sensors. So that's definitely also a cost consideration. All right, so that's the 4 V's definition of big data: volume, velocity, variety, and veracity. And that's also the data types of our world. You know, we have activities data, conversations, words, voice, social media, you know, browsers, image, video, sensors, you know, all different data with the 4 features. And finally, we apply different tools, for example, natural language processing, text analytics, sentiment analysis, face recognition, which is more computer vision or image processing, movement analysis, which is more about the motion analysis, voice, and that's also some machine learning algorithms. And the reason we are doing that is finally with generate value. The value is actually we know better and we can make better decisions. So this is also the framework of the, you know, the information system. Like we move from data to information to knowledge. It's just extremely difficult, fundamentally different for big data compared to regular data. So this is actually a very interesting TED Talks about big data, how big data is changing the way we work. But I wouldn't play them today. I uploaded the slides on the camera system. So if you're interested, you're more than welcome to watch yourself. So guys, let's take a quick break, like for 10 minutes. I just need to take a break very quick. And my throat is actually sore. All right, see you guys in about 10 minutes.